Chapter 1.1 Horizontal and Vertical Translations. Transformations are a process that changes the appearance of a graph. There are three types to explore: translations, reflections, and stretches. These transformations can be found in the form of y equals a f bracket b bracket x minus h close bracket plus k, where a, b, h, and k are numbers called parameters. By manipulating these parameters, the appearance of the graph can be changed. Translation: to move a graph horizontally or vertically. This changes the location of a graph, but not its shape. Compare the graph of y equals f of x to y equals f of x plus k. Example: compare the following graphs: y equals f of x, y equals f of x plus 4, and y equals f of x minus 2 if f of x equals the square root of x. Then write out the equations that describe the functions. F of x equals the square root of x. We could also write that as y equals square root of x. Then f of x plus 4 equals the square root of x plus 4. Or we could write y equals square root of x plus 4. And then f of x minus 2 equals the square root of x minus 2. Or we could write y equals square root of x minus 2. Let's sketch a graph. I can do a table of values. I'm going to sketch f of x first. F of x equals square root of x, the x value and the y values. We saw from our review of functions, this is a radical function, and radical functions cannot have a radicand that is negative. So in this case, x would have to be greater than or equal to 0. Then we start with 0, square root of 0 is 0, x equals 1, square root of 1 is 1. Then let's pick x equals 4 because that's a perfect square. Square root of that is 2, and x equals 9 is a perfect square. Square root of 9 is 3. I can plot those points on my grid: 0, 0, 1, 1, 4, 2, and 9, 3. And then I can join them together with a curve. And that is our function y equals f of x. Then we can graph f of x plus 4, which is square root of x plus 4. Using the same x values, square root of 0 plus 4 is 0 plus 4, which is 4. 1 for x, square root of 1 is 1, plus 4 is 5. Put in 4 for x, square root of 4 is 2, plus 4 is 6. Put in 9 for x, the square root of 9 is 3, plus 4 is 7. Then we can plot those points: 0, 4, 1, 5, 4, 6, and 9, 7. Join those points together with a curve. And this is y equals f of x plus 4. Next we can do a table of values for the last function, y equals square root of x minus 2. Going to use the same x values again. 0, square root of 0 is 0, minus 2 would be negative 2. x equals 1, square root of 1 is 1, minus 2 is negative 1. X equals 4, square root of 4 is 2, minus 2 would be 0. And x equals 9, square root of 9 is 3, minus 2 is 1. Plot those points, 0, negative 2. X equals 1, y is negative 1. X is 4, y is 0, and x is 9, y is 1. Attach those points with a curve. That gives us y equals f of x minus 2. Describe how the graphs compare to the original function. The shape of the graphs hasn't changed, so same shape. The location has changed. They've moved up or down. So same shape, but moved up or down, which is called vertical translation. Another word for translation is shift. So you could also say vertical shift. Then what effect does the parameter k have on the graph of y equals f of x plus k? If k is greater than 0, then the graph is shifted or translated up k units, like we saw with f of x plus 4. The k value is positive 4, and the graph of f of x, which was here, got shifted up 4 units. For k less than 0, so k is a negative, the graph is shifted down, and it goes down absolute value of k units. We saw that in y equals f of x minus 2. It's the same shape as y equals f of x. Looks the same. It's just been shifted down 2 units, and k was negative 2, so that told us to go down absolute value of negative 2 units, which is down 2 units. Compare the graph of y equals f of x to y equals f of x minus h. Compare the following graphs: y equals f of x, y equals f of x minus 1, and y equals f of x plus 3 if f of x equals the square root of x. Write out the equations that describe the functions. So our equations, we have f of x equals the square root of x, which we can write as y equals square root of x. Our next equation is y equals f of x minus 1. Notice this time that the minus 1 is inside the brackets with the x. That means it's going to go under the radical with the x. So y equals square root of x minus 1. And our third function is y equals f of x plus 3. That means instead of x under the root, we put x plus 3 under the root. Sketch the graphs. Y equals square root of x. We can do our table of values again. X and y, this is for y equals square root of x. We're going to use the same values, starting with 0 because we can't take the square root of a negative. Square root of 0 is 0, then 1, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. Plot those points, 0, 0, 1, 1, 4, 2, 9, 3. Join those points with a curve, and that's the graph of our function y equals square root of x. Next, we'll do table values for y equals square root of x minus 1. I want my radicand, the thing under the root, to be 0 for the first x value. So when is x minus 1 equal to 0? That would be when x equals 1. If I started with 0, 0 minus 1 is negative 1, and the square root of negative 1 is undefined. Then I do 1. 1 minus 1 is 0. The square root of 0 is 0. If I do 2, 2 minus 1 is 1. The square root of 1 is 1. Then I want an x value that results in the square root of 4, because that's a perfect square. So x equal to 5. 5 minus 1 is 4, and the square root of 4 is 2. And then I want the radicand to be equal to 9, so x equals 10. 10 minus 1 is 9. The square root of 9 is 3. And plot those points. 1, 0, and then 2, 1, 5, 2, and 10, 3. Join those points together with a curve, and we get y equals the square root of x minus 1. For our third function, y equals square root of x plus 3. Make a table of values. X and y. Again, we want our first x value to give us a radicand of 0. So x plus 3 equals 0. X would have to be negative 3. Negative 3 plus 3 is 0. The square root of 0 is 0. We want our next x value to give us a radicand of 1. X plus 3 equals 1. So x would have to equal negative 2. Negative 2 plus 3 is 1. The square root of 1 is 1. We want our next x value to give us a radicand of 4. X plus 3 equals 4, then x has to equal 1. So we get the square root of 4, which is 2. And then we want our next x value to give us a radicand of 9. X plus 3 equals 9. That means x has to equal 6. And then the square root of 9 is 3. Plot those points. Negative 3, 0. Negative 2, 1. 1, 2. And 6, 3. Attach those points with a curve. And that's our function y equals square root of x plus 3. Describe how the graphs compare to the original function. Again, we have the same shape. All the graphs are the same shape. But this time they are shifted left or right. Which is a horizontal translation or a horizontal shift. What effect does the parameter h have on the graph of y equals f of x minus h? Since the form of the transformation is written as f of x minus h, then h is opposite of what it looks like in the function. So here x minus 1, that means h is positive 1, and we see that our graph from the original was shifted 1 to the right. Then if h is greater than 0, which means our equation will have an x minus h, then the graph moves right h units. And if h is less than 0, then we would have a x plus h in the function, and the graph moves left, absolute value of h units, which is like the second one we did, where we had y equals square root of x plus 3, which means that h is negative 3. Then from the original function, our graph was shifted over 3 units to the left. Mapping notation. There are points on an original graph that correspond to the points on the new graph. This relationship is called mapping. Mapping notation shows this relationship. Example, for a translation that is 2 units up, we can write a point x, y on the original function. 2 units up, that's affecting the y value. That would become the point x, y plus 2 on the transformed function. The y value increases by 2. For a translation that moves 3 units left, that means h equals negative 3, we can write a point xy on the original function would be mapped to the point x minus h, so minus 3, and y on the new function, and the x value decreases by 3. A summary of translations for the function y equals f of x plus k. The transformation from the function y equals f of x, it's a vertical translation. If k is greater than 0, the graph moves up. If k is less than 0, the graph moves down. Mapping notation, a point on the original function y equals f of x is xy. That is mapped to the point x, y plus k for the function f of x plus k. And some examples. F of x is the blue graph in the middle. Then if k is positive, y minus k equals f of x, or y equals f of x plus k is shifted up. And if k is less than 0, shifts the graph down. For the function y equals f of bracket x minus h, that's a horizontal translation. If h is greater than 0, the graph moves right, and if h is less than 0, the graph moves left. The mapping notation, a point xy on the original function f of x would be mapped to the point x plus h, y on the transformed function. We have some examples. Our original function y equals f of x. We have y equals f of x minus h if h is greater than 0, moves to the right. And y equals f of x minus h if h is less than 0, moves to the left. Describe how the graphs of the following functions relate to the graph of y equals f of x. State the h and k values and provide the mapping notation. Y equals f of x minus 1. We have an h value here. H is equal to positive 1. The h value is always opposite of what it looks like in here, and that represents a horizontal translation right 1 unit. Then our mapping notation, a point x, y on y equals f of x, would be mapped to the point x plus 1 y on the function y equals f of x minus 1. B, y equals f of x plus 4, we can write that as y equals f of x minus negative 4. So h is negative 4, which is a horizontal translation 4 units left. Then the mapping notation, a point xy on y equals f of x, would be mapped to a point x minus 4y on y equals f of x plus 4. C, y equals f of x minus 7 plus 5. We have an h value equal to 7 and a k value equal to 5. That represents a horizontal translation 7 units right and a vertical translation 5 units up. Then a point xy on the function y equals f of x would be mapped to a point x plus 7, y plus 5 on the function y equals f of x minus 7 plus 5. dy minus 1 equals f of x plus 10. Let's move that 1 over by adding 1 to both sides. Then we get this function to be y equals f of x plus 10 in brackets and then plus 1. So our h value would be negative 10 because f of x plus 10 is f of x minus negative 10. And then plus 1. So h equals negative 10 and k equals 1. So that's a horizontal translation left 10 and a vertical translation up 1. Then a point x, y on the function y equals f of x would be mapped to a point x minus 10, y plus 1 on the function y equals f of x plus 10 plus 1. Write the equation of each transformed function in the form y minus k equals f of x minus h of y equals square root of x, horizontal translation of 3 units to the right. So we are starting with the function y equals square root of x, and we are translating 3 units to the right. That is a horizontal translation, so that means that h equals, it's going to the right, so h is positive 3. We don't have any vertical translation, so k would just be 0. Then y equals f of x minus 3. Remember, it's opposite. So if h is positive, we write x minus 3 in the function. That would give us y equals the square root of x minus 3. B, y equals absolute value of x, vertical translation of 2 units up, and a horizontal translation 3 units left. So vertical translation 2 units up, that would be k equals 2. Horizontal translation 3 units left. We're going left, so h is negative 3. Then we have y equals f of x minus negative 3 would be plus 3, and then plus 2. And our function is an absolute value function, so we apply that and we get y equals the absolute value of x plus 3, and then outside the absolute value, we have plus 2. You'll often see the k value written on the other side with the y, so you could also write this as subtracting 2 from both sides. You'd get y minus 2 equals absolute value of x plus 3. What vertical translation is applied to y equals x squared if the transformed graph passes through the point 3, 15? So it tells us we have a vertical translation that is a k value, and it does not say anything about a horizontal translation, so that means that there is no horizontal translation. So h equals 0. Then in the function y equals f, x minus h, close bracket, plus k, we can sub in what we know. We have h is 0, so y equals f of x minus 0 is just x, and then plus k. And our function is a quadratic, it's x squared, so y equals f of x is the x squared portion, and then plus our k value. We also know that the graph passes through the point 3, 15. 15 is a y value, so we can put that in for y, and 3 is the x value, put that in for x. We have 15 equals 9 plus k. Isolate the k by subtracting 9. We get 6 equals k, which is what we wanted to know. We wanted to know the vertical translation, so k equals 6, which is a vertical translation up 6 units. What horizontal translation is applied to y equals absolute value of x minus 3 if the transformed graph passes through the point 9, 1? This time we have a horizontal translation, which is h, and we have no vertical translation, which means that k equals 0. Then y equals f of x minus h plus k. If k is equal to 0, we get y equals f of x minus h. Our function is the absolute value of x minus 3. So we have y equals the absolute value of x minus 3 and then minus h. We know that it goes through the point 9, 1, so we can replace y with 1 and x with 9. Then we can simplify. 1 equals the absolute value, 9 minus 3 is 6, minus h. From Math 20-1, we should recall that when we are solving absolute values, we have 2 cases to solve. Case 1 is that the number inside the absolute value is positive, so then we can just drop the absolute value and say 1 equals 6 minus h. We're going to subtract h from both sides. We get h plus 1 equals 6, and then subtract 1 from both sides, and we get h equals 5. Case number 2 for an absolute value equation is that the thing inside the absolute value is negative, so this one was positive, this one is negative. Then if the thing inside the absolute value is negative, we can drop the absolute value by doing 1 equals negative bracket 6 minus h, close bracket. Multiply the negative into the brackets. We get 1 equals negative 6 plus h, and then add 6 to both sides, and we get h equals 7. This tells us that we have a horizontal translation of 5 units right, or a horizontal translation of 7 units right. Either one of those horizontal transformations would result in the graph passing through the point 9, 1. Editing Corey coming at you. For some reason here, I wrote and said subtract h when really I wanted to add h, which is what I did. I have positive h plus 1, so I did add h, but I wrote minus h, so that should be plus h plus h. H equals 5 is still correct because I did the math correctly. I just, for some reason, said and wrote subtract h instead of add h to both sides. Describe the translation that has been applied to the graph of y equals f of x to obtain the graph of y equals g of x. Determine the equation of the translated function in the form y minus k equals f of x minus h. So starting at f of x to get to g of x, we can look at some of our points. To get from a to a prime, this is called, we would have to go from a y value of 3 up to a y value of 6. So that's a vertical translation 3 units up. And then we need to go horizontally from x equals 2 over to x equals negative 6. That would be a horizontal translation of 8 units to the left. So 8 left. This tells us that h equals negative 8 since we're going 8 units left, and k equals positive 3 since we're going 3 units up. So our function would then be y minus k, which is y minus 3, equals f of x minus h, so minus negative 8. Then y minus 3 equals f of x plus 8. What is the domain? So the domain for the transformed function g of x, the farthest left we go is negative 6. So domain in set notation x such that negative 6 is less than or equal to x is less than or equal to the farthest right that g of x goes is negative 1. And then xer, close the bracket. In interval notation, we're going from negative 6 to negative 1. Both of those points are included, so we would use square brackets. What is the range for the transformed function? In set notation, y such that the lowest y value of g of x is point b prime, which is at 3. 3 is less than or equal to y is less than or equal to the highest y value for g of x is 6. And then y is an element of the real numbers. Close the bracket. Or in interval notation, the range goes from 3 to 6, and both of those values are included, so square brackets on both ends. If a point xy lies on the graph of f of x, write the mapping coordinates of xy. So we know that h is -8 and k is +3. Then a point xy that was on f of x would be mapped to x minus 8 and y plus k, which is 3 for g of x. That brings us to the end of Chapter 1, Lesson 2.